Morning.
Morning. Oh, I'm using the wrong one. Oh, good. Morning, Paul.
Morning.
Okay, good.
Hello, good morning, William and Paul.
Hello, good morning, John.
হ্যালো না পাইলে কি আপনি কোথায় কোথেকে পাঠিয়েছেন? ও আচ্ছা বুঝছি, ওই জন্য কইলাম ওকে পাইছি। হ্যাঁ, ও তাহলে তো আপনি ইয়া করে তাহলে আপনি পাঠিয়ে দিতে পারেন। আমারটা লাগবে তো, আমি তো এই যে মিটিং এ একটা সময়। ও তাহলে থাকেন, আমি কল দেবো। আমারটা পাইলে আমার যদি পাঠায়, আমার এখনো পাঠায় নাই, পাসওয়ার্ড ভুলে গেছে। তাহলে আপনি একটা নিয়ে যে আপনি পাঠিয়ে দেন। আচ্ছা, নিয়ে যান তাহলে। হ্যাঁ, ওকে, কারণ আপনি পাঠিয়ে দিলে আমারটা আমি পরে পাঠিয়ে দিতে পারবো। ও কিন্তু আপনি এটাতে প্রিন্টার নিতে হবে। আপনি প্রিন্টার নিচ্ছেন, একসাথে অ্যাটাচ করে একসাথে পাঠাতে হবে। ওটা আমি দিচ্ছি, তাহলে আমার ইমেলে করতে হবে। এটা এডিট করে দিয়ে যেতে গুড। এইটা প্রিন্টার নিয়ে ওকে আমি পাঠাবো, কারণ আপনার তাহলে তো সবগুলো একসাথে পাঠাতে হবে। অথবা আপনি এসে আপনি নিয়ে যান, ঠিক আছে? ও কিন্তু আপনাকে আমরা স্ক্রিন দিয়ে পাঠিয়ে দেবো, ওতে পারবেন না। আপনার সবগুলো একসাথে পাঠাতে হবে।
Okay. So excuse me.
আমি তাহলে প্রিন্টার নিতেছি, একসাথে
Yeah.
পাঠিয়ে দেবো। অথবা আপনি পাঠান, আপনি
Hello, Mr. Azad Bunyan.
Yes,
How are you?
I'm doing fine.
Great.
Hello, Ken. Is it Kenneth? Yeah, it's Kenneth. Kenneth Anderson. Yeah, hi. Hi, Kenneth. Kenneth Anderson.
That's all right. Hey, William, how are you? I was on mute. How's everybody doing this morning?
I thought I recognized your face.
Yes, sir. Good to see everyone.
Yeah, good to see you. Thanks. Welcome.
Hi, everyone. Yeah, it's 11 a.m. Eastern Standard Time by my cell phone, which can't be wrong. So we have to get ready to start the second day of module 3. Again, a few announcements. As I said yesterday, module 8 is a series of current research presentations. And that will not be in 1 week, that will be throughout the week. So the first one will be next week, Thursday at 11 a.m. And the topic is application of data science in COVID-19, and then also data mining in higher education. The presenter is Prem Saga. He is the one who gave the presentation for module 1. Again, live TA sessions are available tomorrow morning, Saturday, 9 a.m. to 10 a.m. Eastern Standard Time. There will be live TA sessions And Sunday, 5 p.m. to 6 p.m., there will be another live session. So for those of you who want to take advantage of that. Other than that, if you have any questions, you post it in Slack, and then one of the TAs will respond to you. So without wasting any further time, I will just hand it over to the two presenters, Paul and then William. Again, if today is your first time joining us, welcome to VADSTI, and then I hope you enjoy this session. All right, Paul, William, over to you.
Okay, so let me share my screen and we'll pick up where we left off yesterday. Let's see here. I can find it here.
Slide 66.
Yeah, let's see here. Get the right one. Let's see if this is it. Yep. Okay, so we stopped yesterday with non-parametric statistics, so that's where I want to pick up today. Yesterday we ended up talking about parametric statistics. Parametric statistics, you recall, are statistics where we make some assumption about the distribution of the both the data and the statistic, and that it follows a theoretical sampling distribution like the normal distribution or the t-distribution, the chi-square distribution. So of course, when we talk about non-parametric statistics, what we mean is distribution-free statistics, or that we're making no assumption about the distribution of the outcome or about the test statistic. And so I've listed here a few of the more common non-parametric statistics that you might see in the research literature. And so like the Mann-Whitney U-test, or that's also known as the Wilcoxon test, that's essentially analogous to a t-test. It's comparing two independent groups. And then the Wilcoxon matched pairs is analogous to a paired t-test. That is, we have paired data. That is data from the same patient, or two variables in which we have measurements on the same patients. The Kruskal-Wallis is analogous to a one-way analysis of variance that we discussed yesterday. And then the the non-parametric correlations are the Spearman or Kendall correlations. And then we also have a test for correlated proportions, the McNealer test. All of these tests are based on ranks, not on the actual data. So for example, if we're doing a Mann-Whitney U-test, we have two, say, treatment groups or two therapy groups, two medication groups. What we do is order the data without regard to which group the particular value is in, and then we divide it into the two groups, Group A or Group B, the treatment group, the control group, and then compare the ranks. So that's where we get the notion of being distribution free, is that we're not assuming any particular distribution about the ranks. The other non-parametric statistics that I want to talk about are the Bootstrap and the Jackknife, because these are very commonly used in statistics. And for the Bootstrap, what we do is we randomly select an observation from our sample data, and it's done with replacement. That is, we might select, from our example yesterday, we might select 5 observations. We compute, say, the mean of those observations, and then we put them back in the data pool, and we make another random selection. And so you can see that that some patients, some observations will be selected more than once, which is okay. The other one that I want to talk about is the jackknife. That's the idea of we leave out one. So we have our sample of data, we compute our mean, and then what we do is we take one observation out and we recompute the mean, and then we do that till we get through the entire sample, however large that is, and then compute the mean of all of those means to get an estimate of our sample mean. So let me illustrate this. This diagram looks familiar from yesterday, except that now that our resampling here, our bootstrap is from the sample, not the population. Okay, so this is the sample of data we get, and so we, when we bootstrap, what we do is we draw a random sample. We draw that sample, we put it back into the original data set, and then we draw another random sample, and so on. And so these now we refer to as bootstrap replicates. And so the statistic here is
they're afraid of the new thing, right? But everything good in life that's going to happen to you is going to require you to try something new. You know, going away to college.
Someone's microphone
Yeah,
is on.
someone needs to mute
Everything new
themselves.
takes some time to adjust to. You're going to
Hello,
feel out of
hello,
place.
someone needs
You're
to
going to
mute
feel
themselves.
nervous. It's going to take you a
Whoever's
moment. You're
listening
going
to a
feel
woman's
apprehensive.
voice.
You're going to be lonely, right?
Oh, okay. So when we draw these bootstrap replicates, and each replicate is, we draw the same size as our original sample. So if we have 30 patients in our original sample, then our bootstrap replicates, each of those have 30 patients in it. But it has, as I say, we do sampling with replacement. And so then the bootstrap replicates form a sampling distribution, and from that sampling distribution, then we can calculate confidence intervals, or we can actually test hypotheses. But you can see that our distribution has no, or there's no theoretical distribution that we're, or no assumption about the theoretical distribution that we're making here. And then the jackknife, where we leave out one, I've illustrated that here with just, say, 10, doing it 10 times. So we have our entire sample here, and so we have a mean that we, for example, or maybe a proportion that we are interested in. And then so what we do is we go through the data and we leave one out. So for example, our first sample here leaves this observation out, and so we recalculate the mean based on these observations. And then we leave the next observation out and recalculate the mean based on these, and so on and so forth. And then we can then get an estimate of the mean and a standard deviation and a confidence interval from our sample, or our replicates where we have left one out. And so as you can see, this can be fairly time consuming, especially if you have a large number of observations to begin with. So those are the bootstrap and the jackknife, leaving one out. And so I think that before I go on, I think that there's an exercise that William has for doing the Bootstrap and the Jackknife. So William, if you'd like to go through that at this time, I think this would be helpful in helping people see what's involved in programming this, which isn't terribly complicated, but it is a really neat way of estimating statistics and estimating confidence intervals. So I'll turn it over to you.
Okay, thank you, Paul. So I'm going to start sharing my video now. I think I might have the ball. Yeah, I can share the video now. Okay, let's see. Give me a moment. Start. Okay. Oh no, I said video. I have to share instead of the video. These things always, technology always hits you, man. Okay, sure. So I'm going to share my screen. If you see it in a moment, give me a moment. Share. Okay. It looks like it's sharing. Okay. So, oh, let's try it again. I think it.
Do I need to stop sharing mine, I guess?
Yes, I think so, Paul.
Okay.
Yes, I think that's it. There we go. Okay. So now we're going to try. There we go. We're going to try again and share. So the orange bar should be around my screen. Still not doing that. One moment. Let's try share again. Okay, let's try it again. So Nana, I don't know. I might have to. Yeah, Paul, you may have to roll me the ball so that I'll be a presenter. Let's see if I can request that. So I've made a request, and
I think the host has to do that.
oh, the host.
Yeah,
okay, it's been flipped now. Good. Okay, sure. So thanks for the short delay there. So as Paul mentioned, we do have the Bootstrap and the Jackknife. So it would be best if we demonstrate that. Paul had these color coded, which makes it easy. So each sample denotes a different color. Okay, so if we go down here, what this is doing is, remember we said we would need a non-paired numeric computing. Okay, so we would run that, and then we need to replicate, to be able to replicate the output. So we use the seed, and then we're going to draw samples. Now to draw samples, if you do this question mark random, okay, so we remember what we said yesterday. If you look at this, it's going to be a little intimidating. So you put a cursor here, and then you go to edit, and then you split, you go to edit, and then you split your screen. I mean, you split the cell. Once you split the cell, you should have access to that portion at the cell, and then you can do this. You can see how what the random does. Okay, so if you do that, Control Enter. Oops, we didn't import yet. So Control Enter here, and then Control Enter, and then it tells you what random does, right? So random, you need the data. It calls it A. You need the size. Whether you want to do it with or without replacement, and at times you can assign probabilities. We do this during office hours. For Paul's purposes, we're going to use just these three. We have a sample, we draw the size, and we do it with replacement. Okay, so now the output is very long. If I try to scroll through with a small screen, it's going to take me a long time. So I just comment this portion, and then I run it again. And then this time, the output will not come. And the output should not come. I don't know why. Oh, there we go here. And the output would not come, and then it takes you to the next cell. Something wrong here. Yeah, there we go. So now we know what a sample does. So all we're going to do is we're going to just repeat that, right? The data is going to, so this is just a test. I want to just see what this does. So let's we'll do this again. We'll split the cell here. Okay. So in here, I'm taking a random sample from this NP array here. Now, when you do NP array, it's just like you saying, "Hey, give me a listing of items from 1 to 10." Okay, so I'm taking a list of items from 1 to 10. I just want to draw a sample of size 3, and I want to do the replacement. So if we take this and we stick this right here, okay, see what will happen. Control Enter. See that? It's giving me a random sample of size 3. I didn't throw in the seed, so the next time I do, I'm going to get different random samples. To get it to repeat, you, as we said yesterday, you would have to throw in a seed so that someone can replicate your output. Sorry. So someone can replicate your output. So I'm just going to do this quickly here. Sorry, I'm taking a little longer than I expected. And now this repeat itself, right? With a seed, it's going to repeat itself. Okay. So that is what this side is doing. This side is just saying, hey, you know what? I know how to draw the sample. I just want to show me how the output looks like. The first sample is going to be of size 3. The next one is going to be of size 5. And it's sampling with replacement, which means that I'm going to have repeated numbers. Okay, so when I do this, okay, now I might have repeated numbers if my sample size is big enough. So let's say I take 51. Now, why would I do it replacement? I'll do it replacement if, let's say my population is smaller than the amount of samples I want to draw from. Okay, that is where the replacement comes handy. If you don't do replacement, you run out of the sample. Okay, so we know how that looks like. So now let's go back and do what Paul has just done. Okay, so what Paul has done is Paul takes a sample. Okay, so I'm going to denote that my output be put into an empty array. And Python, you can assign multiple things on one line. Okay, when it sees the assignment, it's going to take the first one and assign it to this. Take the second one and assign it to this. And take the third one and assign it to this. So this is saying, hey, start with an empty output collector. I want a random sample of size 5 because that's what Paul's output looks like. And I want to do 10 replicates. I want to do 10 groups of 5. Okay, and then all we do is we know how to run through our range. Okay, our range goes through the number of replications, 1 through 10. Each time I take a sample and I hold on to it, and then I take the mean and I hold on to it. I could have done it in one line, but I want you guys to see. And then once I have the sample mean, I just want to stick it on, append it to this group of sample means. Okay, and that's all. And at the end of it, you can do a whole lot of things. But now this is all we're going to do. So I'm going to split the screen here again, and then we'll just run this this output and see how it looks like. Okay, so in here, what happened in here? So if I do this, sorry, let me go up. Something happened here. DPI is not defined, of course. We did reading the data yesterday, and we want it again. So let's go up and read that data. Okay, so, Paul's data is in. Remember, on day 1, we read in the data. So let's go up and read the data. I could have done Control F, but I'm going the way you would do it too. So let me run these guys. Come down here and load my data. Okay, so now I got the data. Okay, so now let's go down and do what Paul did. Okay, to do that, you just go up here and click on the non-parametric, takes you right there. And now I'm going to run that. Run this just in case. Skip this, run this, and now my samples have been computed. How do I know that? I can now print the sample mean in here. I mean the samples in here. So this output now should have my samples. Okay, so those are the output. So those are the sample means. Okay, now I have the sample means, and that is what Paul had done. There are other things that I'm going to skip, so don't worry about this. I'm just going to skip so that we get the same output as Paul. So let's do that here. And then I've got that, and this now becomes my output. So for each of the sample, I'm drawing 10 replicates, and I've got a mean. Okay, so that's all I'm doing in here. I'm taking samples, and I'm drawing the mean. And then at the end of it, I'll just display. So that is what the Bootstrap is doing. Now, when you come to Jackknife, Jackknife is a little exciting in the sense that you leave one out. So as Paul has it here, when I given a sample of X, the first time I'm going to draw, let's say I start from the bottom up, I'm going to draw the index out. So when X is 1, when I'm on the first row, I drop the first sample, the first item. On the second, I drop the second. On the third, I drop the third. On the fourth, I drop the fourth. So primarily, you can play with the index and exclude the data point that matches the index. And that's all we're going to do in here. So here, we're going to do the same thing, okay? We're going to define where we want things to be stored. We want the means, and then we want the replicates. The mean is going to be emptied. The replicate is going to be the length of your data set. Remember, the X denotes the length of your data set. Okay. Now we come down here, and then we basically take the index. Okay. So when I say MP array of replicates, okay, so this guy here, what this guy is going to do, and I always say, always split your screen up so that you can follow it nicely. So I do a split in here, and then I go back here. Now, once you run this, you want to see what index gives you. Okay, so index gives me the number of items in the replicate, this replication, which is the length of DBP, which is about 143. Okay, and it's 144, but Python starts from 0. Okay, so I've gotten the index. So now I can play with those indexes, right? I can now go through the indexes. Each time, if the DPI of index, okay, if the DPI, the index of my DPI is not equal to the index that I'm on. Okay, so how do you know the index of the DPI is not equal to the index you are on? What you do is you take this guy here, okay, and then you do the same thing in here. Split this thing up, come down here. We know what index is. Okay, we know index is 0, 1, 2, 3, 4. So when I is equal to 1, okay, if I say, tell me where index is not equal to I, see what will happen. You're going to get, oh, sorry, it's not equal. So bang, equal. Okay, you're going to get a bunch of true false. So you see that when it's not equal to 1, it says it's true here. If I change this and make it 2, you see that the true will flip. You see? Now, so you can play with this I and index and get to exclude things that you don't want to exclude. So this is saying that it's going to pick everything, but it's going to exclude this 7th item or 8th item. So that's all we're doing in here. So I'm saying in here that whenever the index, which is your I, is equal to the index that you are on, don't include that. Okay, get those items, the true and false. And with the true and false, you can now take DBI of that, okay, and get that sample. So now you've excluded one item. Once you have a sample, computing the mean is trivial. Okay, so you compute a mean, and then you just, here what I'm doing is, I want to see the process as it goes on, but I don't want to display all. So when if I is less than 4, or I is greater than 140, just show me what you are doing. Okay, so let's run that. And you see that this is our original data. When the first index, it excludes the first data point. So your data starts from 42 to the end. And then it gives you the mean. Okay, so this is how, if you don't understand it, this is how I will do it. And then when the index goes to 1, the next item, which is 42, will be excluded. So your data will go for 73, 73, and that's what you've seen here. And it goes on and on and on till you hit the last. And at the end of everything, you got a bunch of means that you can compute a mean, and that gives you that. So this primarily explains what Paul took us through. For whenever X is 1, exclude the first item. X is 2, exclude the second item, compute a mean. 3, do that. 4, do that. This is different from Bootstrap. Bootstrap doesn't leave one out. Okay, Bootstrap computes, create a sample, okay, with replacement and computes a mean. Okay, you are computing the statistic. Get a sample, compute, get a sample, compute, get a sample, compute. At the end of it, then you can compute the means or the statistic that you want to bootstrap on. Okay, so that is what Paul is doing in here. This colors, you are not leaving one out. This one, you are leaving one out. Okay, but the same concept remains. Okay, Paul, I'll pass it back to you now. So I'm going to stop sharing unless anyone has any questions. And we'll cover this during the TA session. You also have this for your homework.
Okay, thank you. I just want to emphasize the point that William made in his code there. You notice the replace command. So when you do bootstrapping, replace needs to be true. If you put replace equals false, then the answer you get won't be correct. Because the idea of bootstrapping is that we replace each observation as we draw our samples to get our distribution. Okay, great. Okay, so let me continue here. I'll get back to sharing my screen. Let's see, I think this was it. Yeah, okay. So what I want to do now is go through a number of topics that we should consider when we do statistics, inferential statistics primarily. And there's no particular order to these, but they are considerations for gathering data, obtaining data, and then doing statistics on it. So the first one is what's known as effect size. And we actually talked about this a little bit yesterday. There was a question regarding this in relationship to when you do your research and you get a sample, whether it's random or not, how many do you need in that sample? And so that's dependent on really, well, three things. The first being what we call the effect size. And that is when you set up your research question and then your hypothesis, how big of a difference, say, between intervention groups or therapy groups or whatever, in the outcome variable do you want to see? Or we might say it's clinically meaningful or important in whatever context you're doing your research. And so the difference we might would be a difference in means, survival rates, a difference in proportions of size of an odds ratio that we want to be able to detect or to show in our research. And then a second thing that we need to know is the variability of the outcome, for example, like a standard deviation. And then the way that we can estimate the effect size is usually you have, you may be doing a pilot study yourself. And the reason you do a pilot study is to get information on how big a difference you might be able to expect, or what, say, the odds ratio or what the proportion might, differences in proportions might be. Or you might get ideas from studies that have already been published, and you're either going to replicate or you're going to do something different, a little bit different, or maybe a lot different. But you can use data that's been published, results have been published, to obtain an idea of estimating the effect size. If none of those work, and I will say I've had plenty of projects that I've worked on where the investigators have no idea of the effect size they want to see or what might be meaningful. So then typically what I might do is sort of a best case, worst case scenario. In other words, given the kind of data that we're going to get, what if there was a difference that was this small or a difference that was this big, how many patients would we need for our study? So typically the number of subjects or the number of patients you have in your studies is primarily driven by cost. But in the way that grants or research studies are judged is basically on the power that you have for your studies, and that's dependent on the sample size. And so in every statistics section, there's a section on how you calculated your sample size and whether it's has enough power to show what you hope to show. Okay, so that's if that gives you an idea of what before you do the study of what you what information you would need. Okay, another concept that I want to talk about is the notion of paired versus unpaired data. When we talk about unpaired data, what we mean is we have data from independent entities like patients in treatment groups or therapy groups. That is, they're independent of one another. The observation of an individual in one group is not dependent on the observation of an individual in the other group. On the other hand, if we have paired data, then there is that association or that correlation between the data, and we refer to that as paired data. So an example of that would be repeated measures data, where we're obtaining data from the same patient over a time period. Paired data also applies to a situation where you've matched patients on some variables, demographic or clinical or laboratory values or whatever you might have. Paired analyses require fewer patients, and typically they have more power unpaired data. And so when we have paired data, we have another source of variability, and we refer to that as within patient variability. Now, if we have both independent groups in the design and paired data, like repeated measures, then we have two different sources of variability, between group variability and then within patient variability. So I want to give you an example of that from a study that we did some years ago.
I'm gonna make some pizza. Do you want some?
Yeah.
No, should I just
I'm
make
sorry.
some?
Dorf, can you please mute? Thank you.
Okay, all right. So this study involved the comparison of percutaneous coronary intervention, PCI, on quality of life in patients with stable coronary artery disease. And the comparison was between PCI and optimal medical therapy, or OMT. And so this was a study that was it was a post hoc study. The main study was to look at whether there was a difference in survival between the two treatment groups. But in this study, we looked at patient-reported outcomes, in particular the Seattle Angina Questionnaire that looks at relief of angina. And then we also used the RAND 36, which is overall survey on health. This is just a plot of the data to show you what I mean by paired data or repeated measures data. So here, and this is for each of the domains of the Seattle Angina Questionnaire. So for example, on physical limitation, we have a means at baseline for the two groups. Then we have a mean at, I think it was 3 months, or maybe 1 month, then 3 months, then at 6 months, and thereafter every year at 12, 24 on out to 5 years of data. And so this is a plot of the means at each time point for the two groups. And so the thing here is that you have patients that have measurements at baseline at time 0, and then the same patient has a measurement at 6 months, 12 months, and so on. Although in this type of research, what you find is that there are fewer and fewer observations or patients available as you go out in time, and that you sort of see that makes sense, that patients drop out, patients die, or for whatever reason. So, but this shows you how you might present, in this case, repeated measured data or paired data. Okay, and so the next concept that I want to talk about is clustered or multi-level data. And so this is sometimes referred to as hierarchical data. And in this case, the clusters are considered what we call random effects. Let me sort of explain that. So when we talk about fixed effects, these are effects that are attributable to a finite set of levels of a factor that are of specific interest to your study. So for example, like treatment groups, sex, race, age groups, say you dichotomized age at 65. So those are fixed effects. Random effects are effects that are attributable to an infinite, or at least a really large set of levels of a factor of which you only have a random sample in your data. And so an example of this might be if you are doing a clinical trial and you're getting data from different hospitals or different sites. Those sites are just a sample of all the possible sites in the universe. You know, obviously don't have data from every possible site. Geographic region might be another example of a random effect. Often you find like clinical trials obtain patients from different countries, different continents even, and so these are random effects because you can't sample from every possible region. Patients and subjects, though, they're always a random effect. So let me illustrate this with the study that I showed you, the Courage trial. So we had data from 3 different healthcare systems, the US hospitals, Canadian hospitals, and then VA hospitals. And then within each healthcare system, we had different sites. So we had obviously more than 2 sites for each healthcare system, but this is just to illustrate the hierarchy here. So we would have multiple sites within each healthcare system, and then at each site you would have patients that were involved in the studies. So here at site 1 we have patient 1 and patient 2, and so on up until the however many sites that we had. And then those patients would be then randomized into the 2 treatment groups, either PCI or optimal medical therapy. So in this case, the fixed effect is the PCI versus OMT treatment that they're randomized to. The healthcare systems and the sites, as well as the patients, are then the random effects, because these 3 healthcare systems are only a sample of all the possible healthcare systems that might be available. And then within each healthcare system, there are any number of sites that we could obtain patients from, but this is usually just limited to sites that are willing to participate in the study. So this is what we mean by hierarchical data. And the issue is that if you don't take this into consideration, then you might get models, or you might get estimates of statistics that are in error or might be misleading. And the reason for that is that data from a given cluster might be correlated. That is, they're not independent. So the issue here of having random effects in your study, probably for the most part, you'll need to consult a statistician about this, because the random effects will complicate the different statistical methods that we looked at yesterday, like regression or logistic regression. Okay, then I want to then talk about non-randomized studies, and where specifically you're doing comparative effectiveness, or you're comparing treatments or medications, or but they're the patients that you are obtaining, that you get for your study, are not randomized into the treatment groups. And this is a situation where more than likely it's impossible to do that, to randomize patients, or it's unethical to randomize, patients. The advantage of non-randomized studies, or what we call observational studies, is that you often have more data, and the data may already exist, like in an electronic medical record. Since the data probably already exists, it's way less expensive to do the study than if you are doing a randomized trial. And then it's also argued that the non-randomized studies maybe gives a more realistic picture of the practice environment, or the real world data, as it's sometimes referred to. The drawback, though, to non-randomized study is that you have the potential for selection bias. And that's because, say, for example, you have two treatment groups, A and B, that are not randomized. That means that someone else, that a physician or an investigator, is making a decision about which patient or which subject goes into which group. So in that case, it's not randomized. It's based on a decision of the investigator, and so then we have potential for selection bias that might confound our results. There are different ways to reduce selection bias. I'm not going to go into any of these in detail, but one way that is often done is what we call matching, or we can do covariate adjustment. So we can say we have our two groups, and we try to match them on different demographic or clinical variables, age, sex, race, comorbidities, diabetes, hypertension, and so on, and match them that way. And then, or we can just include those variables like age and sex and so on as covariates in our regression equation, or in our comparison. Some other ways that are a little more sophisticated and probably a little better to do is what's called propensity score analysis. And also related to that is inverse probability weighting. And then instrumental variables, where you have a variable that is a stand-in, or could be used to represent another variable that would potentially confound the study. So there are different ways of reducing selection bias, but the point I want to make here is that if you do have an observational study, that you can't just do statistics as we discussed yesterday without thinking about selection bias, and in some way controlling for that in the study. In a randomized study, then you don't have to worry about that, because the randomization, theoretically at least, washes out differences like this, different demographic or investigator variables, or lab or comorbidities that would potentially confound your results. Okay, so let me summarize what we've talked about yesterday and today. So our statistics that we have gone over, and the different concepts related to that, estimation, hypothesis testing, are based on the concept of repeated sampling. That is, if you were able to repeat the sampling process an infinite number of times, then you're going to get an estimate of what the true population parameter is, mean or a proportion. This is what's referred to as the classical or also frequentist viewpoint or perspective on statistical analysis. And so when it's based on the idea of repeated sampling over time or whatever, then our results the statement we want to make about the results we get, that they are likely or unlikely due to random sampling variability or chance. And so that's the key to this particular viewpoint in statistical analysis, is the concept of random sampling variability. And then we talked about p-values for hypothesis testing. And in the classical perspective, they're based on a theoretical sampling distribution. And remember, the p-value is a cutoff point that we want to refer to our results as statistically significant, or that we have no evidence for there being a real difference between our groups, or whatever it is we're testing. And so we went over the normal distribution and then gave an example of computing the chi-square for proportions. And then as we just talked about, that non-parametric statistics make no assumption about sampling distributions. And so in many cases, if the data is such, or the statistic that you've calculated is such that you really don't know if there's a theoretical distribution that you can use, then the use of the non-parametric statistics like the Bootstrap or the Jackknife would be a preferred way of looking at sampling. Okay, so I'll stop there with that presentation, and then the next presentation that I want to do, or that was for primary today. Let's see, I think I need to stop sharing this and pull up another one. Let's see if I can find it here. Is this it? Oh, no, that wasn't it. Okay, maybe this would be a good time to take a 5-minute break.
Okay.
While I find my next presentation here.
Yeah. So Paul, is going to be called Bayes' Day 2 PDF.
We're going to look at another perspective of doing statistics that's different from the one that we looked at.
So Paul, I can send you a copy of the file if you don't have access to Codio. On Codio is going to be the Bayesian. It's called Bayes _ Day 2.pdf.
Yeah, let's see. I should. Okay, that should be. Maybe this is it. Yep. There we go. Okay. So what I want to look at now is statistics from a different viewpoint, and it's referred to as Bayesian analysis or Bayesian statistics. This may be new to a lot of you, or maybe not. Maybe some of you are actually Bayesians. But anyway, what I'm going to do is I'm going to sort of go back. I'm going to go back and I'm going to review the frequentist or the classical perspective, and then compare that with the Bayesian perspective. And then I think what I found is the best way to illustrate Bayesian statistics is to actually do some examples. So I've got 3 examples that I'll go through to illustrate how Bayesian statistics are done. And the examples are, I'm going to look at diagnostic testing. Then I'm going to look at a study that was a randomized trial of medications for epilepsy. And then finally, I'll look at what's called probabilistic sensitivity analysis, or it's actually sometimes referred to as Bayesian sensitivity analysis. Okay, so if you remember from yesterday, this was our starting point for classical or frequentist perspective statistics, that we have a population of interest and then we draw a sample, a research sample from that population, and we estimate our statistic, a mean, a proportion, or whatever it is from that. And so this was the illustration that I had where we have a population of interest. There's a population mean, which we don't know, and we're trying to estimate that mean based on our sample. And so our classical viewpoint, or our frequentist viewpoint, was based on the idea of repeated sampling over a over time, or doing a large number of possible random samples from our population. And we talked about if we're using the mean as an example here, that with a large number of random samples of a particular size, that the mean of these means will equal the population mean.
Excuse me, Paul.
Yes.
So, moderator, could you please mute everyone, because it's really very it's not making us concentrate on Paul's talk. Thank you. Sorry, Paul. Yeah. So sorry, Paul.
No problem. Thank you. Okay. And so again, this is just a sort of review of what we went over yesterday. And so here's an example from my diastolic blood pressure. And if I assume this is the 144 of my population, then I can draw random samples, different random samples from this population. And what I get then is that we talked about yesterday was a sampling distribution, where the sampling distribution is now a distribution of means, the means of each of my samples here, where my sample size was equal to 5. And so when I arrange these in order from lowest to highest, and you can see that some of the means are pretty close to the population mean, which was 76, but some of them are not. But this is my sampling distribution of a statistic, in this case a mean. And then we looked at confidence intervals and what that meant from the frequentist standpoint, that a 95% confidence interval means that over repeated sampling, the confidence interval will include the true population mean 95% of the time. And so we looked at my illustrations here, and then this was one of the exercises which I don't know if you got to that yesterday afternoon, but you can see here the concept that over repeated sampling, that my confidence interval will include the true population mean 95 times out of every 100 random samples. but that means that there's 5 times that it won't. And you can see here that I've got a couple in my small number here where the confidence interval does not include the population mean. Okay, and then we applied that to hypothesis testing, where we had want to compare, say, 2 groups, a treatment and control group. And so we wanted to see if the mean of the treatment group of blood pressure of 81 was different, statistically speaking, from the mean of the control group. And so our null hypothesis is that there's no difference, that, or whatever difference there is just due to random sampling variability or chance. And our alternative hypothesis from a statistical standpoint is that the difference here of 5 millimeters of mercury is is unlikely to have occurred just by random sampling variability. And so when we do statistical hypothesis testing from this point, we will either reject the null hypothesis or we'll fail to reject the null hypothesis. And then we talked about the alpha and beta errors, and the alpha error being the traditional 0.05 that you see in most research literature. And then what that means. So for example, if we set our p-value at 0.01 and we get a p-value of 0.05, then it's not statistically significant. We would fail to reject the null hypothesis. And if we set our p-value at 0.01 and the p-value is actually less than that, then we will reject the null hypothesis. But that would mean that we'd be wrong 1 time out of every 100 random samples. And then we talked about what p-values are, what p-values aren't. But this is just a repeat from yesterday. So, and then of course the interpretation of a p-value, that what it means is that when we say something is statistically significant, what we mean is that there's just a small chance that the results we got, or the difference in means or proportions we got, occurred by random sampling variability. Whereas if our p-value cutoff is greater than whatever we set it at, like it's greater than 0.05, then we can only conclude that we didn't find any evidence for a difference. So that's sort of a recap of the classical or the Frequentus viewpoint on statistical analysis. Okay, so let me get into then comparing that with Bayesian statistics. So in the Frequentist perspective, probability is the long-run frequency of random events over repeated sampling. Okay, and so we've illustrated that in sort of different ways. From the Frequentist viewpoint, our data are random. That is, it's a random, or more, it may not be random, but it's a sample out of a population. So the data are random and the population parameter is fixed. From the Bayesian perspective, probability is an index of confidence that we have about the occurrence of an event. In other words, the probability is going to actually be what we think the chances are that event occurring or not occurring. And from that perspective, then interestingly, the data are fixed, but the population parameter, mean or proportion, is random. So in Bayesian analysis, there's really, I guess we could call them the steps that you go through in doing statistical analysis. So in Bayesian analysis, we have a prior belief about the occurrence of something, a condition or an event, a diagnosis. We then get new information, which is our data or our research study, where we obtain observed data. And then based on that data, we revise our prior belief with a new belief, or what's called the posterior belief. And let me give you an example of that. So if we have a physician who's prescribed some medications for a particular patient, and then this patient comes back and gets lab results updated lab results, then the physician may update the medications based on the current lab results. So that's sort of the idea of having a prior belief. You get new data, in this case lab results, and then you revise your prior with the new. And so I use this example because physicians are really Bayesian in practice. When if they're in a position where they actually do research, then they usually become frequentists, but in practice they're Bayesians. That is, they have a particular idea, say like on a medication or on a diagnosis, but they get new information and then that diagnosis is updated. So the foundation of Bayes statistics is Bayes' theorem, which is a statement of conditional probability. And Bayes statistics, or Bayes' theorem, has been around for a long time, 300, maybe 300 plus years. But it really wasn't until the advent of high-speed computing that Bayes' theorem had much use in statistical analysis. But the idea here is that if you want to know the probability of event A, given that event B has already occurred, then that's equal to the probability of A times the probability of B, given that A has occurred, divided by the probability of B. Now, it seems really simple, but there's some really complicated applications of this. But this is really the foundation of Bayesian statistics, is conditional probability. So let me go through some examples here. The first one I'm going to use is an example of diagnostic testing. So let's say that we have some test for a disease. The test can either be positive or negative. And then we have the situation, the true state of affairs, where a person either has the disease or they don't have the disease. And so you can see in my 2x2 table here, which we looked at 2x2 tables in a sort of analogous fashion yesterday. But my first cell here is what we call true positives. In other words, those are people who are positive on the test and they actually have the disease. The second cell here is what we call false positives. Those are people who test positive for the disease, but they actually don't have the disease. And then we have false negatives. Those are people that test negative, but they actually do have the disease. And then the true negatives are people who test negative and they don't have the disease. This actually has a lot of application in the current COVID climate for tests for whether a person has COVID or not. And so the statistics that we can calculate from this type of table, well, the first one we call sensitivity. And so this is just the proportion of those who test positive who actually, out of those who actually have the disease. So that's the true positives divided by the number who actually have the disease, true positives plus the false negatives. Specificity refers then to the proportion of those who are true negatives out of all those who are negative for the disease. And then we can calculate what we call predictive values. And so the positive predictive value is the number of true positives out of all those who test positive for the disease. And the negative predictive values is the number of true negatives divided by those who test negative for the disease. And then we can, of course, calculate a false positive rate and a false negative rate as I've given here. So what I'd like to do, and this just sort of repeats what I've said from the table in words. Sensitivity is the proportion of true positives correctly identified by the test. Specificity is the proportion of true negatives correctly identified by the test. And then the predictive values, positive predictive values, the proportion of patients with a positive test that actually have the disease, and the corresponding negative predictive value, patients that have a negative test and actually don't have the disease. So the unknown here is the prevalence of the disease. And it turns out, the prevalence being, of course, the proportion of disease in a given population, those that actually have the disease. And it turns out that sensitivity and specificity of a test are independent of prevalence. But the predictive values, the positive and negative predictive values, are dependent on prevalence. So, and this is the only really, I think, difficult slide I have here, but illustrating how we use Bayes' theorem to update a prior probability given a specific prevalence. And so what we have is our prior probability is the prevalence, and then our posterior probability that we want to calculate is the positive predictive value. Okay, so we can rewrite this formula here. So this is the probability of disease given a positive test. And so that's equal to the probability of a positive test given that you have the disease, or sensitivity, times the probability of disease, which is the prevalence. And then this numerator can be rewritten in this more complicated form here to be able to do what we want here. But basically, this is the probability of a positive test given that you have the disease, which is and the probability of the disease, the prevalence, which is the same as we have up here, plus the probability of a positive test and not having the disease times the probability of not having the disease. Or this here turns out to be 1 minus specificity. So then we can rewrite our positive predictive value here as sensitivity times prevalence divided by sensitivity times prevalence plus 1 minus specificity times 1 minus prevalence. And then we can do the same thing for the negative. I won't take time to go through that. So let me illustrate this with a table where I've just put in some numbers here to illustrate these concepts. And so let's say that I've done a study where I've looked at some particular test for abnormality or normality, and that I have some gold standard where I can know whether a patient is actually abnormal or normal. And so I've done this on a total of 344 patients, and these are the results that I get. So my sensitivity is that, remember, those are have the positive test and are actually abnormal divided by the total abnormal. So in this case, it's 231 divided by 258, or I have a sensitivity of 0.89 or nearly 0.9. My specificity then is the number of true negatives divided by those who are normal. So that's 54 over 86.6. And then my predictive values, my positive predictive values, those that have a positive test divided by the total that have a positive test. And then my negative predictive value, those that have a negative test divided by the total number of those that have a negative test. And then in this case, my prevalence turns out to be just the total that are abnormal divided by the total number of patients that I have. So my prevalence in this case is 0.75. So let's say that I want to take my test here to a different location, a different context, a different set of patients. So I know my sensitivity and specificity, but let's say that I have a situation where the prevalence is different. And so what if we have a situation where the prevalence is only 0.5 rather than 0.75? And so for my positive predictive value, I just fill in the formula that I had before. This is my sensitivity, this is my prevalence that I put in, my updated information, and then this is the denominator that I have from my formula before. And it turns out that now if the prevalence is only 0.5, then my positive predictive value is 0.7. And remember that in my in the example I had, it was let's see, what was it? Well, I'll go back and look at that later, but it was lower than it was that the predictive value was when I had a prevalence of 0.75. Well, let's say that the prevalence is only 0.25. So then I recalculate that, putting in my updated prevalence information. And now I get a positive predictive value of only 0.45. So you can see that the predictive values are really dependent on prevalence. And you can see that as the disease is prevalence or less common, more rare in a population, your predictive values, your positive predictive values will decrease. The negative predictive values, as you would imagine, will increase. Okay, so that's using Bayes' theorem to update diagnostic tests where you know the sensitivity and specificity but have differences in prevalence. Okay, the second example I want to use is a randomized trial where they looked at 3 medications for status epilepticus. And so they are going to use, well, actually in this study, they use both Bayesian and classical statistics, but I'm going to focus on the Bayesian statistics. So I want to go through their methods and their statistics in a fair amount of detail here so you can understand what they're doing. So they want to compare we'll look at just the efficacy of these 3 anticonvulsive agents. I'm not sure how you pronounce all levetiracetam, phosphenitel, and valproate. So what they're going to compare the efficacy for these 3 different medications, and their way that they're defining their outcome is the absence of clinically evident seizures. And so they're going to calculate the posterior probabilities that each drug was the most, or they also do the least effective. We're just going to look at the most effective. So their outcome, as I mentioned, was the absence of clinically apparent seizures. So it's an either or, a dichotomous outcome that they're looking at, yes or no. And then they also have a safety outcome that they're going to look at. We're not going to focus on that. We're just going to focus on the primary outcome of efficacy. So they use what they call a response adaptive comparative effectiveness design. So the comparative effectiveness here, I've used that term before. We're comparing these three drugs. The response adaptive, I'm not going to go into that, but basically what that means is they initially randomize people in a equal fashion, that is a 1-to-1-to-1 in the 3 drug groups. But after 300 patients, they then did the response adaptive thing where randomization was based on what the previous response to the outcome or to the drugs was. So they're changing the randomization scheme as they go along here. And then they do what are called interim analysis after 400, 500, 600, and 700 patients. So at each interim analysis then is when they change the randomization assignment. And they also then stratify the randomization according to age, which makes sense. And then this statement here is really key in doing Bayesian analysis that they are going to make the prior assumption that all three drugs were equally likely to be the most effective or the least effective. So the response rates then were modeled independently with the use of Bayesian analysis. And so their prior probability, their prior distribution is what's known as a uniform distribution that can take values between 0 and 1. And so their posterior distribution is a binomial distribution that is updated from the data that they get, and then they compare the three distributions in a posterior manner. The uniform distribution is what's called a non-informative prior, and so what is meant by that is what they state up here is that they're assuming to begin with that all three are equally effective, and that would be, I'm representing that here by bar graphs where the three drugs have an equal percentage or proportion of effectiveness. So in doing Bayesian analysis, then what they did is they took randomly selected from their posterior probabilities to calculate that a probability of a given treatment was better than the other two. And they did this, their iterations were, they did 1 million iterations each time. That's quite a few. So the comparison or their probability statement here that would be analogous to a p-value is that their criteria for declaring a most or least effective treatment was a probability greater than 0.975. And this was just chosen arbitrarily. They're basing it on the classical alpha level of 0.025. So what they're saying here is that what they want to show is that one treatment is better than the other two treatments, and the probability of that being true is 0.975. Okay. And then they give their reasons for coming up with those numbers. So their effect size here that they're looking at, they define effective as a 15% difference. So they're hypothesizing that one of the medications would have a 65% true response rate, and it would be only 50% in the other two. So here's their definition of their effect size. And then they're going to report this as a percentage, and then they're going to calculate intervals, but in Bayesian statistics, these are called credible intervals, not confidence intervals. And we'll sort of look at that, look at the difference in interpretation of each. And then so they mentioned that the primary analysis is based on the intention to treat. That is, even if a patient didn't get the drug that they were assigned to, they're analyzed as if they actually got that particular drug. So what I want to do here first, before I show you the results, is I want to show you what their alternative hypothesis is. And this is actually what they're going to do. They're going to plot, or they're going to plot the distributions, the posterior distributions that they get in doing their 1 million iterations. And this is what they want to show. And so this would mean that the group there that I've outlined in red, the probability that this is 15% greater than the other two is 0.975. And so what that would mean is that in our distributions here, we could have a 2.5% overlap in the distributions, and they would call that significant then, okay? So that's what they were hoping to find, or what they wanted to show. So here's their actual results. And so here they've plotted their distributions for each of the drugs. And you can see that there's hardly any difference between them, that they're pretty much right on top of one another. So their conclusion is that there's no difference between the three drugs as far as being superior, one being superior to the other. And then they, in their legend here, they give the credible intervals, the 95% credible intervals for each of the three drugs. And so I've reproduced them over here, and you can see that the proportion of being more efficacious than the other two are essentially the same for all three drugs, and their confidence intervals are pretty much overlapping. And so their conclusion is that there's no significant difference. Okay. So in terms then of how we interpret Bayesian and Frequentus intervals, in Bayesian statistics, it's referred to as a credible interval. And a 95% credible interval, for example, means that there's a 95% probability that the interval includes the population parameter. From the Frequentus standpoint, though, the confidence interval means that over repeated sampling, the interval will include the population parameter 95% of the time. Now, that's it may not be obvious in terms of how you might, or there is a huge difference in how you interpret the difference in the credible interval versus a confidence interval, because they mean different things. What you find, though, is often people who do Frequentus statistics interpret their confidence interval as a credible interval, but that's not the case. So as we had pointed out before, the Frequentus is based on the idea of repeated sampling, whereas from the Bayesian perspective, we're giving a actual probability for that the interval includes the population parameter. We're not going to sample the data over and over again. Okay, the final one that I want to go through is a really complicated analysis, probabilistic or Bayesian sensitivity analysis. And this is a situation where we have multiple input variables to estimate multiple parameters, outcome parameters. And this is used when parameter estimation is sensitive to changes in input variables. In other words, it really kind of depends on the value of your independent variables or your input variables, what your results are. Give an example of this. In this case, the prior, and then I'm going to give an example here, the prior and posterior distributions are coming from the same distribution, whether it's a normal, a gamma, beta, but we might have just different distributions for other variables. And so in the example I'm going to give, which I need to give a little bit of explanation of, is in cost-effective analysis. And the idea here is that what we're interested in is not just whether a treatment or therapy or whatever is more effective than another one, but we want to see if it's what's called cost effective. In other words, the reasoning behind this, of course, is that there might be something that is really better than another treatment, but the cost is so high that you can't realistically administer the treatment. So what we have in this case are patient-level costs and patient-level measures of effectiveness. And in the example I'm going to give, the outcome from the study is at the lowest level, just survival. And that is how long a patient survives given the treatment that they received. And we compute this we change this into life years gained, and then we transform those again into what we call quality adjusted life years, or QALYs. And those are calculated by multiplying life years gained by some utility, which is scaled from 0 to 1, 1 being perfect health and 0 being death. And then we also have, for individual patients, the cost of treatment, which would be the procedures, if they needed a coronary artery bypass, for example. There would be physician costs. There would obviously be medication costs, maybe hospitalizations after the procedure. You might have office visits, lab tests, and so on. So there's different things that go into determining the cost of a treatment. But I want to give an example here from a recent study we did, and where these costs come from. You have to tell people where you got these costs. So, for example, for a fatal cardiovascular event for age 45 to 64, the mean cost was $18,940. And then over here is the reference we have for that, because you can't just pull these costs out of thin air, although I think some people think that they are. But anyway, so we have a mean cost here that we're going to use in our cost-effective analysis. And we have a distribution for this cost. And it's costs are usually assumed to follow what's called a gamma distribution, which is a distribution that's right skewed in comparison to a normal distribution. And then we have costs here for different age groups for a non-fatal MI. And so those are the costs. And so we, if you were to draw or plot a histogram of costs, you're going to invariably get a distribution that looks like this. And you can see that it's right skewed here. And the reason, of course, it is right skewed is that you have extreme costs out here. Most patients would have costs within a certain range, but you always have those patients that have costs that are really far outside what's usual. But we need to include these costs because they're potential real costs in our analysis. And you might say, well, why don't you just do, say, like a log transform and make this normally distributed data? Well, the problem with that is if you log transform it, you get a graph that looks exactly like this because of these extreme values out here. They'll still be extreme in log values. So that's we're assuming this kind of distribution for cost. And then for effectiveness, we have different utility values. Remember, these are values between 0 and 1. And depending on if they've had a history of angina or a history of myocardial infarction, stroke, then they're assigned a utility of this, and then their life years gained is multiplied by this number to get quality adjusted life years. And again, we have a distribution for these, and generally it's accepted that they do follow a beta binomial distribution. And I'll just mention here, disutility is sort of the idea, which is a controversial idea, that if you experience any of these during the trial, then this amount gets subtracted from the utility that you were originally assigned. So that gives you a little bit of the idea of the data that we're going to get. And then the statistic that we're interested in is what's called the incremental cost effectiveness ratio, or the ICER. And this is just the difference in cost between treatment A minus the costs in treatment B divided by the effectiveness in treatment A minus the effectiveness in treatment B. And so a typical dollar amount here, or an amount that's sort of accepted as tolerable, as cost effective, is a ICER of $50,000. And so what that would mean is that for every $50,000 you spend on treating whatever it is we're doing here, or whatever procedure it is, that we gain one quality adjusted life year. Okay, so when we get our differences here, our cost, a mean cost and a mean effectiveness, then we plot those in what's called the cost effectiveness plane. And so over here in the upper right quadrant, we have what's called the cost effectiveness quadrant. That is, costs are higher, but so is effectiveness. And so we would want to determine how much we're going to have to pay to gain one quality adjusted life year. Quadrant 2, which is what everybody hopes for, is that not only is the treatment effective, but it's also less than whatever the standard is. And so we call that dominant, that the treatment dominates the standard of care or the control. Then we have the situation in quadrant 3 here, where cost is less, but so is effectiveness. And then sort of the worst scenario is where not only are costs increasing, but effectiveness is less. And so we call that dominated, that whatever the treatment is not only is it less effective, but it's also way more expensive. So what I want to illustrate here is how then we do the Bayesian analysis of this, because we have different costs for different events. We have different utilities for different histories. And so what I've tried to depict here is a random draw from these different distributions. And so if we do 100,000 random draws, and say, for example, our first one, we have a patient who has a stroke. They're taking atorvastatin, and they have had a history of angina. So that would go into computing our cost for this patient and the quality of life. Now, I need you to understand, this is not a real patient. This is a hypothetical patient, but the cost distributions and the utility distributions here are based on our observed data. And so we do this a large number of times. In the example of epilepsy, they did 1 million draws. I don't know that you need to actually do that many, but that can be quite time consuming. So anyway, what you end up then with is, however many times you do this, we can plot something like this, where we plot, or a graph like this, where we plot the mean cost difference by the mean effectiveness difference. And so we can then draw a contour plot here, where the inner is 90% of all of our random draws fall in here, 95% within this ellipse, and 99% in the outer ellipse. And then I drew the line here where there's no difference in effectiveness. The cost is always higher, so there's no zero horizontal axis or vertical axis here, I mean. But we can see that it's not particularly cost effective, as the mean of all of these is close to zero. So that's a way of doing a fairly complex Bayesian analysis when you do cost effectiveness analysis. So to summarize, from the frequentist perspective, that's based on repeated sampling of data from a population. And the confidence interval means that over repeated sampling, the interval will include the population parameter a certain percent of the time, like 95% or 99%. From the Bayesian perspective, we have a prior distribution. We get our data, and then update our prior distribution with the posterior distribution. And from a Bayesian standpoint, the credible interval is a probability statement. For example, a 95% probability that the interval includes the population parameter, which, as I pointed out before, is different from the concept, from the Frequentus concept of a confidence interval. So just to summarize the, and this is sort of my opinion, basically, if you have simple or straightforward analyses, although they can be kind of complex, but you're probably better off using Frequentus methods because they're easier to use, they're easier to set up, and they're a lot faster to run. But if you have a really complex multi-parameter analysis, then it's difficult for Frequentus methods to, handle those, like the last one I gave on cost-effective analysis. So I have on the last slide here some references. The first one is the trial that we looked at with the 3 meds for status epilepticus. The second one is actually a textbook. It's a fairly readable textbook on doing Bayesian analysis if you're interested. And then the last one is a journal article that gives a kind of a nice comparison of credible intervals and confidence intervals if you're interested in that. Okay, so with that, I want to thank you for your time and attention, and I think we have time left over here if William has any other things that he wants to go over, or if you want to ask any questions or with anything that we've talked about the last 2 days, we can take the time that we have left to go over those.
Yes, Paul. So I think your suggestion is very good. We do have office hours. We have 4 hours of office hours. So I would suggest that if there's anything in the statistical aspect that is not very clear, I would take advantage of this time and ask Paul, because Paul will not be available during the office hours, but we will. If you understand the statistical concept, pulling it into Python is really straightforward. So let's concentrate on the statistical. If you don't have any question, then we can just go to the office hours and run through the assignments and then give you time to go and look over it, and then see you tomorrow morning. I think we do have office hours Saturday and Sunday, and then we also have one today. So it's up to you and the organizers. I would say let's take advantage of Paul's knowledge in statistics and master the material that Paul had presented, and then we'll make time for you during the TA office hours, or when we completely have no other questions.
Okay, so if you think of questions later on and you want to email me, here's my email address, so feel free to contact me if you like with any questions or any issues. We've covered a lot of territory, and we've covered it briefly, and we haven't gone into any detail about specifically doing things like linear regression or logistic regression, but some of the examples using the data that I have that William has prepared, I think would be really useful in sort of understanding what you're doing when you do statistics. And that's sort of the point of my presentation, is to sort of help you understand the concepts, not so much to make you statisticians or being, wanting to actually do the computations, yourself.
So John, what did you just take? I think the original plan was that if there are no questions, we'll go and we'll give students some time to look at the problems, and then we'll get back and go through them. Okay. One other option could be that some students don't even know how to, haven't mastered the Ipython environment yet. So we can run like a 5 to 10 minutes overview of your keyboard shortcuts and what the homework, the expectations of the homework, and then let you go and try it on, and then we'll come back. So it's up to the organizers. Which direction do you want us to go now?
Yeah, if there aren't any questions, if you want to take the time to go through some of the other examples, we can do that now.
Okay, thanks a lot, John. Oh, there we go, John. So John, yeah. So we've come to the successful end of mod 3. There are no questions. So the idea here is that students are going to be shown what the expectations of the assignments are, and then we'll stay on for anyone who wants to stay on. Students will go try it, and they will be around, and then we'll get back to them. I don't know if that has changed yet.
I would say, I mean, if the student, if you need to give them maybe, because we have about 45 minutes left, if maybe they have to spend 15 minutes to try kind of hands-on on the pattern, then they come back at 1 o'clock, then maybe we use the last 30 minutes to complete it.
Okay, thanks a lot. Okay, so let me just show you what the expectations of the assignment is, and this is basically going to cover day 1. If you know how to do the day 1 and you've mastered the material that was presented today, Bayesian in general is a hard topic, so I won't worry too much. If you don't understand it, you can go back, reread it, watch the video, and then you implement it. So we look at what the expectations of the homework is, and for the benefit of people who haven't used the Ipython environment, I'm just going to go through this quickly, and then as we ask you to try it on your own. Okay, so let's go back to the we'll go back to the Codio. So if you go back to your Codio, you see something that looks like this. Okay, so in your Codio, which is a student file, yeah, we went through. We basically went through the top portion, loading the data, running the sampling, doing the inference, and we went through all this. We went through it very fast. So the expectation is that you pick up from the 4th and 5th. So we didn't do the regression. So go through the regression exercise. Okay, the same way using the data that was provided. Okay, and then just go through the questions as they've been asked, and then we'll come back here and do it. And then when you get back to the non-parametric, it's also the same way. We went through this briefly. Just try and fill this out, and don't get too stuck. If the question is too long, I realizing it now, I should have probably broken it up. But that would also help you experiment with Ipython environment. You place your cursor here. If it's too much text, go to your edit, split up your view, and then solve that portion. Okay, and then come to the next portion and solve it. What I've done is I've given you keyboard shortcuts. So if you look in your in the mod 3, there would be the keyboard shortcuts that will come handy. I will go through the top 3, which is the control. Your control and the shift are going to be your primary keys. Okay, control means you are taking control of the Ipython environment. Control enter says, hey, don't proceed. I want you to do it and I want to see it. Shift enter, you giving control back to Ipython so it will do it and go. So that's the way I perceive it. Control means take control. Shift means give it back. Okay, so we're going to have these controls. Controls are going to allow us to fix stuff in our Ipython environment. What do I mean by that? So in here, if I get stuck and I want to experiment with stuff, just hit the plus a couple of times and you have your own little Ipython prompt. Okay, so in here, if I say A equal to 2, B equal to 3, and for some reason I've got some more text that I don't want to run all this. All you do is you highlight this, okay, and then you hit a control slash, and it's commented. Control slash toggles, okay? So that's how you comment blocks, control slash. And that would allow you to run this, because the thing is, if you don't have the control slash, then this is going to throw an error, okay? So it could have been that you're trying to import something that you couldn't import and it's throwing you an error. One way would be to split the screen. Another way would be to just block it, control slash. Alternatively, someone would just come in here and put an asterisk, asterisk, asterisk. That's a waste of time. Control slash, and that's what the shortcut key is. Okay, and then the control enter says, hey, I've fixed the cell. I want to see if the output, if my fix worked. Okay, so throw in some print, and I do my control enter. If I don't use control enter and I use a shift enter, the shift enter will move to the next cell. Okay, so control enter will fix it. And then once I'm happy, then I release a control, I hold down the shift and I do an enter and it takes me to the next cell. Watch out, when you see this green, the green means the cell has not been executed. Okay, that means you are in it, you haven't executed. If you execute it, the color will change from green to blue. It means I've executed it. Even though I've executed a cell, once the cursor comes back to it, Ipython says, well, we've done it before, but now back. You haven't done it. Since you clicked, you made the cell active, you haven't executed. So all you do here, control enter or shift enter, and it will change. The blue says you've done it. Okay, so blue says here that I've executed it. There's nothing in here, but you've executed it. Okay, so that is what the expectations of the homework is. Take your time, go through it. The markdown is going to throw people off, but don't be too much thrown off. What a markdown does is, once you markdowns are there for independent for research. How do they say, presentation? Just like LaTeX, you've got your code all over the place. You want your report to look nice so that you can present to management. How do you do that? You do that by putting in tags, what we call Markdown. You can Google Markdown and find out. We can do it during TA sessions. But to toggle between Markdown and the command, you see here, the code, you can have a Markdown and you can go back to code. When I go to Markdown, what do you see? You see there's no coding. Now, what Markdown does is I can have here, and people who have taken Econ 181 knows, we use it to actually ask them to send their assignment. So in here, I could have something like William, okay, and see what will happen. And then I could also have, let's say, lead tech analyst, say, if I can type analyst. Okay, analyst. Okay, bear with me, I'm just, okay, now see what will happen in here. If you hit Control Enter, it's going to error, okay? In this case here, it executed, everything is commented, nothing happened. Nothing is happening here. But let's say I go in here, I've gone to, let's say, a Google site. Let's say I go to a Google site and pull some materials. Let's say I do a Google, and let's say William Ampere. Okay, so let's say I go to William Ampere here, CSI. Let's go down here. I just go pull some material for William. So come over here, Control C. I come back to my Ipython, stick this text here. Okay, so I've got some material that explains what I'm going to do. Maybe I'm going to take the square root. Maybe I'm going to do something. If I try to run this, we're going to get an error. The comment will be fine, but the text will error. Okay, it doesn't know what to do. What I intended to do actually to make this a markdown block. Okay, and you see that thing change. Now in here now, the text have been formatted. So this is how I document my work. So let's say I am going to question one and I'm going to compute the square root. So I tell the person I'm going to give this material to is that, hey, you know what? The next cell is to compute the square root. So I document my work, and then when I do that, okay, I hit Control Enter, see what will happen. You see, you have a nice formatted document that looks just like a LaTeX document, or it looks like a material you can send to your boss. You don't have to then cut and paste your report into Word. Okay, you can just have this in our Markdown, we call it knitting. In here, you can actually save it as an HTML. You can save it. You can primarily export it as a PDF, a LaTeX. You can export it in so many forms. So your work becomes a final product. You don't have to do a cut and paste. Okay, so that's what the Markdown component here is. So if I'm in the code section and I want to flip to Markdown, it is escape and an M. Okay, as you change. Escape and a Y. We're getting back to the code. Okay, so those things you find in the lecture 2. Those are the shortcuts I would say worry about. The rest of the code, even if you don't understand it, we'll come back to the office hours and take note. I put a shortcut key somewhere in here. You have the shortcut keys somewhere. I will repost them if we don't have them. Let's see. Let me go back here and repost them. So the shortcut keys are here. Copy, and I think it's down. Sorry. Let me go down. Oh, sorry. Just one moment, and then we'll allow you to just go try things out. Okay. So the shortcut keys are here. Okay. I'll post them here again in case the tests are gone. So we did. The shell is called the Ipython. So if you hear people mention about Ipython shell, what it is it is this thing here that you see. Okay, this is the shell. Okay, there's something behind it, so that when I do my assignment, it takes it from the IDE and sends it to the shell, and then I can ask the shell, show me what a plus 2 is. Okay, a plus 2, and Ipython will give it back to me. Okay, so that is what the expectations of the homework is. Take your time. Don't get too bogged with trying to understand this in one day. Most likely, it's not going to happen. The reason being that this is an advanced level, even beyond an advanced level course, and you're taking this semester course, you're taking it in 2 days, less than 2 days. I mean, 4 hours or less than 3 hours. So just take time, follow the material. The material is going to be made available. You come back and try it out again, but painstakingly make sure that you understand everything before you go on. That's what this exercise is for. Reading the data and then taking this data and linking it up to the statistics that drives the data. Okay, so yeah, so that is the expectations. We're going to ask you to break up and or even hang in here, but try it on your own. Okay, so click on the link and it will take you there. I've given you the slide numbers. I'm giving you the expectations, and then we'll give you the prompt, give you some little information, and ask you to proceed to try and get something that matches the output. Okay, so thanks a lot, and we're going to hang around and for the next 15 minutes, so that will be about 1:15 roughly. We'll get back. Yeah, thank you.
And also by way of announcement, especially for those of you who may want to leave early, I make sure you complete the survey forms. I believe that is posted in Slack. Nana or Stacy, I don't know if you want to also post it in the chat area here. So again, the next module or the next instructional module will be in 2 weeks. But next week, there will be a 1-hour presentation on research topics. And then the first presenter is Prem Saga. The topic is on data science application to COVID-19 and then data mining in higher education. So that will be just 1 hour of your time only on Thursday. So those of you who can make it, look out for the invite, the same way the other invite was sent. You have to look out for that also. So William is here for the next few minutes. Those of you who are struggling with Python, I see one person saying that I'm still struggling with Python and I'm not yet keeping up. So maybe you can send, I don't know if you have time to go to the office hours tomorrow, but William will be here also to answer those questions.
Yes.
Hi, excuse me. I have a question. The office hours. You indicated that in the chat, right? You put that in the chat where I can just call in if I need to, or are we zooming into it?
Yes. So we do have the TA, and Stacy have been kind enough to do that. Let me share that. That's a good point.
Okay.
I think making that known. Oh, sorry. Making that known would help. So let me do that. That's a good point.
Okay. And William.
Let me share that. Yeah, let me share that. Because I think it will make sense a lot if it's very transparent, so that we don't come here and then we don't see anyone. Because it takes a lot of effort to come. Okay, so if you go to Slack, right? If you haven't seen this already, an invitation was sent out for the TA channel. If you subscribe to if you did in mod 3, somewhere up here you see something that says a TA channel is available. I think Stacy would. There we go. Here, you see there's this office hours.
Okay.
If you click on it, then this TA channel will be visible. And then once you come to the TA channel, the office hours, I think we made it very. We actually did add. I added it last night, but I'm going to add it here again. So TA session under mod 3, or even in general, I think we also added it in general. There we go. Yeah. So if you come to general, and then what Stacy is going to do is Stacy will make available a WebEx link on the TA session page. I think they've already been created. So just pick the WebEx section that corresponds to the day of the week. Okay, so this one here says office hours, and it will give you. It gives you this. This is the one that was that we had yesterday, and there's going to be one for today. There's going to be a link that Stacy will make available for today, and there will be one for Saturday and Sunday as well. So come here. If you don't find it, just post an announcement. I just post something in mod 3, or post it. Target me or Stacy or someone, Nana, and Nana will get to me, or just put, hey, when is the next? What is the link to the next? Yeah, just put something on Slack. Slack is your go-to place. Anything, just and there's always someone looking out for you.
Okay, I have one more question, William.
Okay.
I was able to do my own Jupyter. I went to Anaconda and installed Jupyter, and once I did that, I noticed that in Python, I had to also include the Ipython in order for me to do a lot of the different coding. A lot of it came out, which is fine. I actually had to go to W3 to look up more information to help me to understand more in detail. But I realize now Ipython does have a little bit more accessibility when it comes down to being able to answer the questions in the different assignment that you gave us.
Yes and no. Because see, the thing is, when you say your own environment, is it a Codio or is an in-house installed Python? Is it something that you had on your?
Well, I downloaded it also. I have Codio, but I also downloaded Anaconda.
Okay.
So I can get into Jupyter, and once I got into Jupyter, I had Python, and in Python, I had to install Ipython in order for me to actually do the assignment. And then it came out okay. But just to let you know that I'm on the right track.
Yeah, so let's talk to Nana. Because normally with Codio, and that's why Nana had this set up to make your life easy. So if you come to Codio, I mean, if you're doing it in class, because the idea here is that we didn't want you to struggle outside class. So this is completely set up, and then you click on this, you would have, oh, sorry, I don't want to publish. If you're a student, I'm not a student, and I've modified, sorry. I've modified this file.
Just you use the blue one.
Use the blue one?
Yeah, click on it.
Okay.
No. Cancel.
Let's cancel that. Okay. Because I've modified my.
Yeah, just click on it again.
Click on this guy again, or the blue one?
No.
This guy.
Click on the module 3. Yeah.
Yeah. Okay.
And use my latest version.
Oh, my latest version. Okay. I added a little bit. Yeah. So once you do this, you're going to get something that looks like this. And in my case, it's going to look. In your case, it's probably going to look like this. Okay. So the first time you're going to see something like this, and then you look for the Ipython Notebook. Okay. And you see it with the IPYNB, Ipython Notebook. If you double click on it or single click on it, it's going to open. So then you don't have to do any installation. The only time you want to do installation is if you want to tinker with stuff like I have. What I have done is I have my own in-house installed version of Jupyter called Jupyter Lab that does more than Jupyter Notebook. But for this class, I think the idea here is that we don't want you to struggle with it. So you just use a Codio. And then if you want to go beyond Codio, we can do it during office hours. So I think for now, so that you're not far behind, I would go through Codio, open it, and if you have a problem in here, then we can have you share your screen and I can help you out.
Okay.
Right. So this will be the line of least resistance. So
Right.
Because you're struggling with two things. You're struggling with the statistics, you're struggling with the code. You want to be able to at least make sure that you follow the concept, and then when you go home, you can extend that.
Well, see, that was the problem. I was struggling in Codio, but when I went to
Okay.
my own system, I didn't have a problem. What I was struggling with in Codio is when I tried to go to the database itself, it was not acknowledging it when I began to put in and to do the different coding, because it could not find the DB. The database itself. Yeah.
Okay, no problem. So can we try now? When you say the database, is it database at work or is it the data that we are working with now? We have two things.
Well, when you load the DBP. Okay.
Right. Oh, the DBP. Okay.
Yes.
You couldn't find. Okay.
Right. When I loaded the DBP and put the code in to get a mean, it would not acknowledge the code because it could not find the DBP file. So that's where I loaded it my own Jupyter, and it worked out fine.
And it worked out. Okay. So can we try this? Can you share your screen if you don't mind, and then we'll do the Codio, because I think others might also benefit from that. And then the rest who are not following us, please just do your work. So yeah, Nana is here, and I'm sure if it's something, because you're going to need this for future modules. So the earlier we fix it, the better, and then we can come back. So let's see. Nana is going to pass you the ball. Stacy. So you are Helen. Okay. So let me see. Yeah, Helen. Let me see if I can pass you the ball. Yeah, Helen. Yes, I can pass you the ball. Okay. So H. There we go. So Helen, I passed you the ball. You get something on your screen. Just accept it. And then you will be able to share your screen. I'm going to stop sharing mine. Okay, cool. Okay, so the share will be in the bottom of your screen. You have the mute, the stop, and the share. Right. And then we'll be able to follow along.
Sorry, I have to get the screen.
No problem. No problem. Oh, good. Okay.
Are you in there?
Yes, we can see you now. Yeah, we can see you.
All right. So. So Nana, could you? I think Helen is probably not in her Codio. Helen, do you have your Codio? Yeah.
This thing is doing a download. 32%. It's going to slow you down. Yeah.
What's downloading?
Okay. Do you see me?
We see something says day 15.
Day 15. Okay, that's my other screen. Sorry, I got the wrong screen.
So, yeah, if you have two
Double-
screens, you want to
Okay.
make sure, you show the
All right,
right.
you
There
see
we
it
go.
now?
There we go.
All right.
Yes.
All right.
Okay,
Okay, so to start with, you need to click on not trusted and make it trusted. You see that says not trusted
Not trusted.
on the next
Yeah.
to Python
Okay.
3. So click on that
Uh-huh.
and click on the
Okay.
trust.
Okay.
Okay.
So you think that that's what it was?
So try it again. Let's see.
Okay, let me go down here. That's not there.
most likely you haven't imported. Yeah, so let's do the import. And at times when you have a small screen size, I normally won't use I won't do like what you're doing. I'll just go to the in here, click in here, and hit Shift Enter. I'll use a Shift Enter to go to the next cell.
Oh.
Okay, Shift. Otherwise, the mouse, because you have a smaller screen, the mouse. There we go. And then do a Shift Enter again. Shift Enter. Good. And do a Shift Enter again. Okay. And do a Shift. There we go. And now we are here. Hopefully, we don't have to install anything. But if we do, then you have to comment out the exit. Okay. You have to put a pound in front of the exit. For now, we're going to assume everything works. So let's do a Shift Enter and go down. And then when we get an error, we'll come up here. Okay. And do a Shift Enter again. I left this blank cells for you to do your own work and do a Shift Enter. So yeah, so that's just, and this is a blank cell. So hit a Shift Enter. Yeah, Shift Enters are better. There we go. Now it takes you right here. Now let's try Shift Enter, and then we'll just address. Yeah, Control Enter. Hit a Control Enter. Because we have an error. We don't want to go past.
Yeah.
Okay. And that gives you an error. So that means that we need these packages. Okay, so let's go. Now we go up to where we were about to take out the exit. There is a shortcut key for up. There is a shortcut key. I've forgotten about it. Right? Yeah. No, use the mouse. Use the mouse and go up to where you have. There we go. Here, click inside it. Click inside it, and now you can use the up and down arrow to move around. So move up. Move up a couple. Okay, click inside where you have the green. There we go. And I'll take out the exit. Put a pound at the exit.
From the exit.
Yes, that says don't stop. The exit is saying just tell me what you are doing and stop. In your case, we don't want to stop. Now go with Control. Go with Shift Enter. I know this will work. So otherwise, you have to use Control Enter. Shift Enter. Go. And you wait a little bit because installation is happening.
Taking place.
Yeah, installation is taking place. So the installation will take place. If it's not coming, I'll be a little worried because there should have been at least an echo.
Right,
so,
telling me installing package.
Yeah. Okay, there we go. There we go.
Okay.
There we go. And that is why I put the installing package so that it tells me there's something happening, so I don't have to hit it multiple times. Okay. So now once that works, you don't want to use Shift Enter anymore. That is it. You want to keep going down. Yeah, you want to keep going down. So keep going down. No, where you have the blue little marker, the Ipython. Yeah. Right here. And now there we go. Now in here, you click in the 2, click inside that Ipython cell 2. Click, and hit a Control Enter because we want to make sure the error goes out. There we go. So now you have the libraries and the packages all loaded, and now you can proceed with a Shift Enter one at a time. Control Enter stays. Yeah, Control Enter leaves you in the cell for you to fix your error. Okay, so that I don't have to bring my mouse up and down. It leaves me in there until the output goes away. Okay, so now in here, you can use a Shift Enter to come to in cell 8, and now you can use a Control Enter because you had a previous error. We don't want the error. we want an output. Okay, so it says now there's a problem here that DBP, you haven't read DBP. So let's go up one. Go up one. I think we've taken that out, but I'll show you how to fix that. Yeah, click inside here, inside the 5. Click on the plus. It's going to
Click
throw
on the
in
what?
the plus, the addition, the plus under the file. The plus next to your scissors. As you go up, you see you have a disk, a plus,
And
scissors.
and
Oh, right here.
Yeah, that's
Yes.
right.
Here. Gotcha.
Good.
Okay.
And in there, we're going to read the DBP. So just say DBP equal, okay, DBP equal, and then we're going to use good equal, and then we're going to use NP, Nancy Paul, NP dot array, okay, and then open parent, close parent, okay, and inside it put a PD like Paul David dot read underscore Excel underscore Excel, open parent, close parent, open close.
Okay.
No, don't go behind it.
Oh,
After the
okay.
Excel.
Okay, I got you.
Yeah, we leave that. Yeah, we leave the other one alone. And
Okay.
inside there, we're going to pull the data. So put a quote, double quote, and in there hit an uppercase D for David, and hit a tab, your tab key.
Okay.
And there we go. And now you can go down and pick the data.xls. So this way, no, data is the data XLS, is the data
Gotcha.
file.
Excel file. Okay.
Yes. Okay, this is how I look for my data. I try not to memorize it.
Ah.
Okay, move your quote, move your cursor beyond the quote. Before the first close parent.
Gotcha.
And put a comma.
Okay.
Now this spreadsheet contains this file contains 2 spreadsheets. We're going to pull the sheet name equals 0. So sheet SEET underscore name equal 0. Okay, and then go beyond the close parent. Go beyond all the close parents. Go beyond that. Yeah, and put a dot. We want to make it look nice, so we put a reshape. We'll talk about this during TA session. And then open parent, close parent, reshape. RESH. You want to reshape it.
Okay.
And then open parent, close parent, -1. -1. And then we want to look at the data. So go to the end of it and hit enter. And then you hit print DBP. Yeah, hit enter, return. And then we want to look at the data. So you can just type DBP. If you, the only time, well, if DBP was, if there's another print after that, then you put a print. If there's no print after that, then you just leave, you just type the name of the variable, because your output will not be overwritten.
Okay, so.
Okay.
DBP. Okay, so just hit run. Oh.
No, DBP. We want to look at it. Yeah, we want to make sure. Okay, and then hit Control Enter. There may be an error, so we don't want to go down. Okay. Control Enter. There you have your data. Okay. Now you can do your Shift Enter and go to the next line. Cool. Yeah.
Excuse me, what does the reshape -1 do?
Yes, the reshape -1. Now PD is appendix data frame.
Yeah.
If we don't do that, then we have to use functions that are known to the pandas data frame. Okay, now we don't want to use heavy function on the simple data. So we want to use the NumPy and internally built functions like the sum and the length. So we just take it back and put it in the NumPy array. And that is what the reshape does. Now, what I would do is I would, instead of a reshape, I would split the screen up, do it without a reshape and do it with a reshape, and you compare the data types. Okay, and you see that one is appendix if you don't put a reshape, it makes it funny. It doesn't formulate well. Reshape basically turns it into a one-dimensional instead of a multi-D. And we'll do this as during the TA session.
I guess what I was trying to ask is what is the argument as -1? What does that do?
Oh, the -1 primarily says take any dimensional data and turn it into a 1D. So I don't, it helps. I don't have to say take a 1D and make it a 1D, take a 2D and make it a 2D. I guess it take whatever dimension and make it a 1D. Okay, so I don't have to be specific as to what is coming in. All I want is take whatever I'm giving you and make it an array, and that's what the reshape is.
Okay, thank you.
Okay, and you can do a question mark reshape, and that would also give you a hint. Primarily, if you have a data frame, and a data frame is a table, right? So you have a table with one column. I don't want a column. I want that column to be wrapped around into like an array. So that's what you use a reshape for. Okay. And if you look in the student cell, you see that I've given you an example of how I would have done it if I haven't read it from a file. So the equivalent of what I've shown you, the equivalent of that reshape is what you see up there. The one with the array with the question mark. Yeah. So the equivalent of the reshape is the data that you see up there. Okay. It turns it into basically a one row of data instead of a one column. Takes a column and turns it into a row. Okay. And here, see, I'm not using any pandas type functions. So I don't want to carry my pandas database around. The read Excel allows me to read Excel file easily. I don't have any way of reading it beyond that PD. So once I've read it, PD has given me, and I have other tools to take it from another form, from the PD form to another form. And that's what I'm doing. And you see a lot of this in Python because you have a lot of tools that does a lot of different things. So you get one tool to do one good thing and then take another tool and turn it into a form that you like. Okay, so you see a lot of these things like. Okay, so I think we got an error there. Let's look at what the error is saying there. So yeah, this is fine. Your 9 is fine. So put the cursor in 9, in cell 9, hit Shift Enter. It will take us to the next cell. Good. And now we computed the mean, okay, which is very simple, sum and length. Now we want to print the mean, which is what we did. But you see what I'm doing here? The reason I went back to NumPy is because NumPy has a method called mean. And it will only, so this type of function will work for, it doesn't need a heavy duty data to work on it. And that is one motivation for me to turn it into an array.
When I did the standard deviation, I did the same thing with NumPy.std.
Okay, so let's try that. Yeah. So go down a little bit because we can't see your screen. So you got a mean. Okay, now let's go down and compute the other statistics. Shift Enter. Shift Enter. Oh, you're computing the standard deviation. Now you import only once. So don't.
Gotcha.
Right, you don't import
I have
only
to do that more than once. Okay.
Yes, it's there in your environment now.
Okay. It already knows.
It already knows, yes, because this is your environment.
Now, what I do like what you did when you did the summation, because at least you broke it down into more detail than just do like a standard deviation.
That is it, and that is exactly what these cells are for.
And that's
they allow you.
I need to get something. When I went to W3, I didn't see that as far as how you did the sum and where you got those codes from. Right. Yeah, I always go baby steps. In fact, what someone can do, since you are in here, I'll go back to line 12. Go to line 12, I'll show you something. Okay.
And then hit a plus. Hit a plus.
Hit a
Okay, so
plus?
we're going to throw in, we're going to throw in a blank cell.
Uh-huh.
And in
Okay.
there, we want the standard deviation. So let's call it my underscore mean, my underscore mean. That is your mean. Okay, comma, my underscore STD. Okay. My underscore. Let's make it local. Let's make it our variable names. So my underscore STD. Just like we did the my mean, we want to do the STD, my underscore STD.
Okay, my underscore.
Yeah.
Oh, instead of me. Okay.
No. You got a mean. That's fine. We want the same thing for standard deviation. So we want my mean, my standard deviation.
Okay.
So my mean, comma, my standard deviation.
Do I
Now
put it here?
take the STD out.
Okay, gotcha.
Comma,
Uh-huh.
space. I want to leave a space so that I can see that there are two variables. My underscore STD. So I'm going to compute two things on one line, and that's the beauty of Python. Equal.
Equal. Uh-huh.
Yeah. And then you put a square bracket. It's going to be a list. Okay. Or even no square bracket. It will error, and then we'll fix it. Take out the square bracket.
Okay.
And then type the formula for the mean, which is numpy.mean BP. Okay. So assuming you want to use that. .mean.
Okay, NumPy. I didn't hear the other part. What did you say? NumPy, right?
Oh, dot mean. Just so we dot mean BP. And then comma dot mean BP. BP. Sorry, DBP.
Okay.
Dot mean of the data object.
Okay. Now, with mean and DBP, do I need a space in between that? Or
No, it's a function. It's a function. It's just like line 11. We just repeat line 11. Yeah.
Oh, I don't need parentheses. Okay.
Yeah, you need a parenthesis. You do need a parenthesis around the DBP.
Okay.
Yeah, sorry. Yeah. Okay, and then put a comma. Now close it and put a comma. And then do the same thing for line 12. numpy.std dbp.
This is the line 12 right here.
Yeah, just copy that. I'll just copy that instead of typing.
Okay.
Yeah, copy it, leaving the equality and just. So we want the standard deviation. No, okay, cool. And let's paste it there. It's it's no. You want to put it on the where we were. So go to where we were after the numpy $mean. You want to add the standard deviation to that line. So you're doing two computations and you put it into two variables.
Okay. So I want to add the computation to this line. So I want to this information.
numpy.std. So where you are, that is it. Copy.
Okay.
Yes. Yeah. Sorry, the communication is a little.
I hear you quite fine. I just.
No problem. And I naturally I talk loud, so I'm not being mean to you. Okay, now hit control. I teach a lot of classes, so I talk very loud. Okay, hit control enter. Cool. Now at the end of it, okay, so click at the end of the close print, and then we're going to print the two variables. So hit enter, and then type my underscore me, hit enter, type my underscore std. We want to display the output. And hit enter, and type the same thing for the standard deviation, my underscore std. And then hit control enter. You get the last value. Okay, and that is the reason why you put a print. The mean came, and then the standard deviation came and overrode it. Okay, because they write into the same output line. So you put a print around the two. So that is why I'm saying if you printed more than one item, then you put print around it. If you printed only one item, then you don't put print. So go back to 14 and put print around my mean and my standard deviation.
Okay.
Last two lines, yeah. Close print and open print in front of it. Yeah, we want to print it. No, we want to print. So let's put a print. Yeah, put a print in front of it.
Okay.
So take the parenthesis, take note, and put a print in front of it. print in front of each line. No, not at the end of it.
You are putting it after. It says in front of it, before the mine.
Oh, I'm sorry. I had to
Yes,
bring it up.
yes,
Got
yes,
you.
yes.
Put
So
it
sorry
in
for that. Yeah, sorry.
front.
Print, and then open print. No, we're doing just like we did on line 12. We're going to print the mean and the standard deviation. So you have a
just like
print
you did
for the
line
mean.
12. Okay.
Yeah, similar.
Okay.
Yeah, print and go to the end of it. Go to the end of where you are and close the parentheses.
Okay.
No, at the end of the line. You want the mean. Yeah, you want the mean to be inside the function. You see, open parent, close parent is an instruction. It says do something. Now the question is, what do you want it to do? You want it to print something. Yes.
Print my meaning. Got you.
Right.
Okay.
Now, let's close that. Do the same thing for the standard deviation.
Okay.
Okay. So put a print in front of it. Yeah, that's it. Open print. And you don't need a space. It's a function. So let's close the space. Yeah, you don't need a space. Right? And then at the end of it, close. Okay. And we'll leave it like that. And hit Control Enter.
Okay.
And you see, the reason I told you don't need a space is you don't want to do extra more typing. So the print will take it with a space or without a space. But this re-emphasizes the need to put print if you are doing more than one output. Otherwise, you see the last one. Yeah, you only see the last one. So with this,
if I'm reading this and I'm trying to explain something, and I'm saying right now, I want for my mean and my STD. In NumPy, I want the mean and I want standard deviation. So I want to be able to print those two items, so I'm able to print individually.
That is it.
In the same area. What do you call this little block? What's this block called? The same.
Oh, this is a cell. This is a cell. Yeah, there's the Ipython Shell and there's the output. The output is at the end of it. So this primarily, someone would just do like you did in line 12. They'll compute the mean, store it, compute the standard deviation, store it. But we are computing the mean and the standard deviation on one line, all together, right? It minimizes keystrokes and it makes your work clean.
Okay.
Yeah, you have one line instead of multiple lines. Yeah. And I like using my. The mines are the variables that I am defining or I am creating. So that if there's a function called mean, I don't confuse that function with the variable that I'm creating. So you see a lot of mine. That's the way Okay, so
Okay, so it's 1:30 now. So this is some of the things you benefit from if you go to the live session. So you want to take advantage of that. Again, the next one is tomorrow morning, 9 a.m. Eastern Standard Time, and then Sunday evening, 5 p.m. Eastern Standard Time. So have a good weekend, and then we'll see you all on Thursday.
I think I want to have something.
We're finished?
Yeah, please take some time to complete the survey. It's very important.
Okay.
Thank you. Please complete the survey. So the videos will be on be uploaded on YouTube by the end of the day. So you can do a playback, okay?
Yes. Nana.
Yes.
Now I'm kind of confused about the survey issue. I missed out doing the survey for previous model. Where do you go to see the survey? The link.
The link is in the WebEx. It's in the WebEx chats.
Can one do the previous survey as well?
John, can you answer that?
Can one do the previous survey for previous model?
No, that is closed. That is closed. You want to do it right after. Yeah, unfortunately, that is closed.
Okay.
Oh, that's okay. But just click on the new survey and just do it.
And so one more thing, I didn't find the attendance sheet, so I have to. Before I didn't do also. So how can I get all attendance sheet?
I'm sorry. Can you say that again?
Attendance. Remember, you sent me
attendance. The attendance sheet. It's in WebEx. Hold on.
It's set to go to the exit. So if I click this one, okay. I started, and last week I didn't do it. I missed the first lecture. And also, you said I don't need to download the Python. I already download the Python today. So anyway, so I can work on the Cordio, right?
Yes.
Yes, and also I'm totally, hello?
Yes, I'm here.
Yeah, something happened wrong. Okay. Totally new, actually. I would learn to learn. So I can, office hour, tomorrow I'll be there and I can learn it, right?
Yes, and we have the TA sessions also. So if you can come online, when you click on the TA channel, then you can join the TA session.
It's Tuesday it's Tuesday, Thursday, and Saturday.
Yes.
Okay.
It's Eastern time.
Okay. Eastern time. Okay.
Yes.
So should I have to go to the attendance thing? How can I? Okay, maybe I can do it tomorrow. Okay, I'll find out.
That's okay. That's okay. So by going forward, the link, just make sure you do that.
Okay, thank you. Thank you, appreciate.
All right.
Okay, bye-bye.
Thank you all for coming.
Okay, thank you. Take care.
All right, take care.
Okay.
Oh, I got it here. Okay.
Bye-bye. Are you gonna hang out for a second?
Do you have a question?
I'll be here.
Yeah, I just have one more thing to show you. I'm just curious because you see this right here? I was trying to do, and I don't think that's what the question was. It was like plot the distribution of the DPN data. This is a map, a scattered plot, and I wasn't trying to use map with that. And this is a different plot. I mean a different plot.
I would say that looks great to me because when someone says plot their distribution, it's normally the density. So that looks good to me. Now, I don't want to take the candy off, but if you go to where it says instructor code, you see a little instructor code below the figures in the left pane. Okay, in the left pane under module 3 slide.
No, she's showing locally installed.
Yeah, I was just trying to locally install. I mean, I could put it on.
Okay.
I could put it on Cordio. It's just that I tried that, but
this is a local. Okay.
But because I wasn't hooked up yet.
Are you? First, you have to make sure you install all the libraries.
Right.
Okay. All right.
Yeah.
All right, because I wasn't quite sure if I was doing. If you were asking for when you said distribution plot, did you want a scattered plot or did you want just a regular like Seaborn, like I had installed Seaborn on.
Yeah, that's Seaborn. Now you see here the idea is that you want to have a peek at your data. So we weren't very specific. We just said in my case I just threw in a histogram plot. With a density plot on it. So this is fine. And then when you see these warnings, for the most part I'm fine with it. I mean unless I'm giving the material to someone. This is just a rough work, so I try not to bang my head too much. This is basically saying you're using a function that will be depreciated. It doesn't mean it's an error.
Okay.
And if I get this and I want to fix it, I just copy the text, stick it on Google, and you see that they give you specifically what to do. They'll ask you to do pip install of a package, which in this case is So normally once you see the error, you don't copy the path. Don't copy the path. Just take it from future warning. Just copy from future warning to the end and stick it on Google. And, they will just answer it. Yeah.
I understand now. Okay.
Yeah.
And also, this you can find the instructor manual on the GitHub channel.
Right.
So everything is there.
GitHub channel. Yes. Okay.
Yes.
All right then. Thank you so much.
Okay.
All right. Well, have a good weekend.
All right. You too. Bye-bye.
Yeah. Thanks. And sorry for my loud talking. Sorry.
Oh no, it's fine. It's fine. I mean, I used to do directing, TV production, whatever, and I was loud. All of that. So I get it. So I understand, but definitely.
No problem. I get too involved in these things. So sorry.
But that's great that you're passionate about it because I do a lot of snipping, so I do snippets So I copy a
okay.
lot of what you're doing while you're doing it at that time, and then I try to
Okay,
apply it
okay.
later on. So
Okay.
that's how I've been managing to keep up.
Okay, no problem. So we'll
All
see you
right,
on
I'm the one.
Saturday.
We'll
We'll see
do.
you.
Saturday
Yeah, we'll
sounds
see you
good,
on
9
Saturday.
o'clock.
Okay,
Okay.
thanks a lot. Okay, bye
Thank
bye.
you.
Have a nice day.
Bye-bye.
Yeah,
Thank you.
okay. I see David. David, is there anything you want to give a shout out to before we kick you out?
No, I appreciate you, William, and I basically will attend tomorrow's session with you. Everything is
Okay.
running properly, and I just want to. The next homework after this one won't be until the next module, right?
Yes,
Okay.
yes. And then David, what I also suggest, I didn't throw in the Bayesian because I thought it was going to be too much work. So if you're down with this, you can actually Google the material that Paul presented, and Google for how to compute those sensitivity and that, and try to mimic that, because everything can be done in Python.
Mm-hmm.
Yeah, so just look at it and then just Google and then try and implement. But normally when you re-implement it, whatever you're missing comes in, it comes back. You see the vision, and then you see the material in another, in its other form.
Mm-hmm.
Okay, yeah. So that's the way I would do it. I mean, that's the way I did it. I read the material and took it one line at a time, one page at a time, implemented. The first time wasn't good, but the subsequent times were good. And then you have a reference material that matches the lecture slide, because the material is good. It just is heavy, especially the second lecture.
Mm-hmm.
Right, right.
All right.
So that would be my advice. That one is not covered, but the idea is that we won't be able to go through everything. So give you guys enough material so that you can expand on that. Yeah.
Okay.
Okay. Cool.
Okay, thank you.
Okay. Thanks
All
a
right.
lot, Nana.
Okay, bye.
Okay. Bye-bye. Bye.